Can you?
Okay. Is Faulkner from the University of Illinois, and is going to talk about some new results on reflected entropy. Please.
Okay. Can I start?
Sure.
Okay. So, well, thank you very much for having me. Sorry about the technical difficulties on my end.
Maybe you can put your slides at full screen, if it can help.
Yeah, okay. Okay, let's try. Oh, no, that's not what I want.
No, that's...
Okay. Let's see, window. Window. Oh, come on. Okay.
Probably is view.
Oh, it's probably view. Okay. Ah.
Last one.
All right. All right. All right, very good. So I'm going to tell you about some work in progress. So I'm going to talk about one paper that will come out soon with my students Simon Lin and Shovik Dutta. And there's another work in progress that I will. Oh, sorry. Oh, it's two slides now. Okay, that's not, okay. All right. Good. And then there's another work in progress that I will not have time to talk about, but I might advertise. So the plan of the talk is I'll review what this concept of reflected entropy is. I'll introduce it for matrix algebras, and then I'll talk a bit about it in quantum field theory, where it's related to the split property. And then, perhaps the biggest motivation for me, at least for studying reflected entropy, is for studying it in ADS CFT, and it has an interesting geometric dual. So the first paper is the subject of which is free massless chiral or Dirac fermions. And in this paper, we give some evidence that, okay, so the reflected entropy, let me just briefly describe what it is. It's related to, at least in a quantum field theory, if I have two regions A and B that are space-like separated, then I can define this reflected entropy. And as those two regions come very close to each other, they almost touch, then we give evidence that this reflected entropy, and more specifically the spectrum of the reflected density matrix, approaches that of the thermal density matrix of the system, where the temperature is determined by the temperature in this setting is determined by the cross ratio of the boundaries of those intervals. The second paper that I won't have time to talk about is the subject of which is entropy in just in finite quantum mechanics with Hilbert spaces of finite dimensionality, and studying this reflected entropy quantity in that, and looking at, in particular, at random states, random pure states, computing the reflected entropy. And basically, the interesting thing about this is to try to find a situation where the reflected entropy jumps discontinuously, which is something that happens in ADS CFT. So this model was good enough to do that, and that's the subject of the other paper. Okay, so let me start with the review. So reflected entropy is a simple computable measure of correlations in a bipartite mixed state. So if I'm just talking about quantum mechanics on finite dimensional Hilbert spaces, then I can talk about density matrices. If I have a bipartite system, I have A and B, and then I could think about a mixed state on AB. Then in that context, I can define this reflected entropy. So it's defined as the von Neumann entropy of some density matrix that I'll call rho AA star. And that density matrix is the density matrix associated to the canonical purification of rho AB. So rho AB is a mixed state, but I can think of it as a pure state in a larger Hilbert space. And in particular, if I just double the Hilbert space, then there's a canonical purification, which you can think of as just the square root of the density matrix. And this is like a vector, this notation I'm using. I'm thinking of this matrix as itself a vector in the Hilbert space of matrices on the Hilbert space, on the original Hilbert space AB. So that Hilbert space is doubled. So we have A star, B star. And then in that, so root rho AB is a pure state, but then I can reduce it to A star, and then I get this rho A star density matrix, and the reflected entropy is just the von Neumann entropy of that. Okay, so let me just sort of give some properties of this quantity. So if the reflected entropy vanishes, you can prove that the density matrix is necessarily factorized. So it's just a rho A tensor rho B. If rho AB was to begin with a pure state, then you can show that the reflected entropy is just twice the von Neumann entropy of rho A, just the reduced density matrix on A. You can show that it's bigger than the mutual information, which is this quantity determined in terms of von Neumann entropies. Another sort of property that you can prove is that if I replace the reflected entropy by some Renyi version of the reflected entropy, so I defined this using the von Neumann entropy, as in minus trace rho log rho, but if I replace that with the Renyi version, minus log trace rho to the n over n minus 1, then you can prove that the reflected entropy is monotonic. So if I increase B, then the reflected entropy will increase. And this is, but you can only prove this for integer n. Integer n bigger than 1. You can show that this quantity is monotonic. The case for non-integer n, and in particular n goes to 1, which is where you go back to the von Neumann entropy, which is what I really call the reflected entropy, is open. It's possible, it's a conjecture. It's actually required for me to, this property would be required for me to prove that it's a correlation measure, which is what I said before, although I put measure in quotations, because of this issue. Okay, so another important thing that we'll be talking about today is the spectrum of this density matrix, rho A star. So there's a spectral decomposition. It's normalized, trace of rho is 1, so they sum up to 1, and so I just get these probabilities pi. And from that, of course, you can easily calculate the Renyi entropies. So perhaps, here, these are some properties. They may or may not make it an interesting quantity to think about on its own. But for me, I think the most interesting aspect of this SR comes from its relation, firstly, to quantum field theory and the split property. And in this context, it's useful as a regulator of entanglement entropy. And the other motivation for studying this quantity comes from ADS CFT. And so I'm going to go through these motivations now. Okay, so the first one, in quantum field theory, if I have two causally complete regions, which I'll call A and B, they're space-like separated, then we expect that the algebra of operators that I'll think of as a von Neumann algebra describing the region A should be contained in the commutant of the von Neumann algebra of the operators describing the region B. Yes?
There is a question.
Question, okay. I cannot see questions, so thank you. Yes.
Yeah, so the definition of rho A star was very quick for me. You said square root of rho AB is the canonical purification. Is that just GNS? Yeah,
it's just GNS, correct.
Okay, yeah. Okay, thank you.
Yeah, I should have said that. To some audience, I can say that, and that's fine. But yeah, yes, that's right. Yeah, so it's GNS, and the important point is that we can find an A star region sort of canonically and compute the entropy for that. Okay, is there any more questions?
No, you can go ahead.
Okay, so the rigorous version of this of the tensor factorization property that I was using to define this quantity before is the split property. So it's known that the von Neumann algebras associated to these causally complete regions describing quantum field theory should be type 3-1, which means that it's impossible to define an entropy for that and so-called entanglement entropy for that because there's no trace. But if we're in a favorable situation with the two regions like this, A and B, then we can find a type 1 factor that lives in between these two. And the idea is that maybe we can use that to define the entanglement entropy, the von Neumann entropy of that. Okay, and the existence of this type 1 factor is known to hold under very general conditions. So, for example, if the high temperature thermodynamics is well behaved. Now, there are many type 1 factors in principle between these two, but there's a canonical one constructed using a state. So if I have some a vector in the Hilbert space, if I have some cyclic and separating vector in my Hilbert space, and it's cyclic and separating for the union of AB, for the two regions AB, then I can use sort of modular theory to define the modular operators J and delta, and then I can use J to mirror A. So I just define this n psi as the algebraic union of the algebra of A, and then I mirror A with JAB. So the first claim is that this type 1 factor that you define in this way in quantum field theory is the sort of continuum version of this reflected entropy that I just defined. And so to see that, if we go back to the matrix algebra, then what we're interested in is the reflected entropy, which is the entropy on this AA star factor. So we should think about the algebra associated to that, which is just bounded operators on HAA star. In the context of matrices, I can define this JAB operation just to take matrices to the dagger of those matrices. Then it's not hard to see that JAB acting on the bounded operators of HA just gives me B of HA star, and so this indeed constructs n psi indeed constructs this quantity, and so the entropy of n psi is the reflected entropy in this matrix setting. Okay, yeah. So n psi is the continuum analog of AA star. So good. So the nice thing about this being a type 1 factor is that there's a trace on the type 1 factor, and I can talk about density matrices. So rho n psi exists. It's normalized, and so we should also be able to find this spectrum pi and summing up to 1. One thing is that we'll use this spectrum. We'd like to use this to define a von Neumann entropy, which would just be then the sum over pi log pi, but it need not converge. That sum need not converge, although the Renyi entropies for n is bigger than 1 will always converge. Sorry, but okay. Good. So now the question is, how do we compute this quantity? So the first answer to that is in ADS CFT, we gave a prescription for computing this quantity. I'll state it as a conjecture. We proved it using the replica trick and things that are not entirely rigorous. Of course, ADS CFT is also just a conjecture, so it can be part of that conjecture. good. Okay, so the conjecture goes as follows. So firstly, let me tell you very quickly about ADS-CFT and entropies in ADS-CFT. Firstly, there's ADS-CFT is a correspondence between gravitational theory and a class of interacting quantum field theories. And it comes in many flavors. There's examples in many dimensions. Let me just stick to two dimensions. So if I think about the CFT side of this, it's a two-dimensional CFT, 1 + 1 dimensional CFT, and at least a class of those CFTs. And there's a correspondence between that and gravitation and a gravitational theory in asymptotically ADS-3 spacetime. So here's a picture of the duality. I'm just sort of schematically drawing a time slice. So if we look at t is equal to 0, a time slice of ADS. Now ADS itself you should think of as describing the vacuum of the CFT. Excitations will be only asymptotically ADS. But in the vacuum of the CFT, we can think about computing quantities, correlation functions, or entropies. And there is a beautiful prescription for calculating the entanglement entropy of some region A. So the entanglement entropy is just the von Neumann entropy of the reduced density matrix that describes A. Now, we know in quantum field theory that doesn't really exist, but bear with me for a little bit. So if A and B are, say, regions on the boundary like this, that are space-like, then one thing you can always associate to A and B are minimal surfaces. These are surfaces that fall into the bulk. So the bulk is inside the circle, and the boundary is you can sort of think of as where the CFT lives. This time t is equal to 0 slice is described by of ADS-3 is just a two-dimensional hyperbolic space. So in particular, there's sort of infinite volume near the boundary. So these AB minimal surfaces are defined just to end on the boundary region. So the boundary region here that I'm drawing is just a space, an interval on the t is equal to 0 slice. The previous regions that I talked about were causally complete regions. Here, they're sort of essentially equivalent to each other because I can just take the domain of dependence of the region A, and as long as everything lives on one time slice, then there's a sort of unique way to go from causally complete regions to just intervals like this. Okay, so now this minimal surface is called the Rutakinagi surface. And Rutakinagi made a proposal that the entanglement entropy of region A which is this von Neumann entropy, is computed by the area of this minimal surface divided by 4g Newton. And so this looks like the Bekenstein-Hawking entropy. There's corrections to this formula, but it's believed that this formula is correct when g Newton is small. But of course, you go ahead and calculate this quantity and you find the answer infinity. And the reason for that is because there's infinite volume near the boundary of hyperbolic space. So that's not actually inconsistent with what I've said, because it does compute the von Neumann entropy of the quantum field theory. It's just infinite, which is sort of the natural thing that you would assign to the entropy of a, say, type 3-1 factor. Okay, so now so the situation I just drew, had, we had two intervals A, B. It turns out that if I wanted to calculate the entropy of A, then I just use the red curve. If I wanted to compute the entropy of AB, then I would sort of sum the two curves together. But if I take the A and B very close to each other, so A and B almost wrap the entire circle, then the minimal surface, there's a sort of a smaller minimal surface which connects between the A and B intervals. So that's shown here, these red curves here. And the Rutakinagi conjecture is that that's the quantity that now computes the the entanglement entropy of the AB region. Of course, it's still infinite, but it's a different minimal surface. Now, in this setting where the minimal surface sort of connects between the two disconnected regions AB, so this region is now a connected region, I can define something called the minimal cross-section. So, firstly, to define that, let me define RAB, which you can think of as the entanglement wedge. So RAB is this space-like region that lives between AB and the minimal surfaces, MAB. So homologously, it's defined homologously. So the boundary of AB is just MAB union AB on the boundary. So RAB is called, so as I said, RAB is called the entanglement wedge. And within this context where I have these two space-like space-like regions on the boundary, I can define a cross-section of the entanglement wedge. So the cross-section is a minimal cut that bipartitions the RAB into two regions here that one I've shaded and the other one I haven't, in some specific way, in a way that makes it a minimal surface, with the condition that it ends on this other minimal surface. Okay, and so now we have some other minimal surface. We can assign an entropy, quote unquote entropy, to that by computing its area and dividing by 4g Newton. Good. Now the interesting thing about this is that it's now finite, and the reason it's finite is because this blue curve never goes up to the boundary. Okay? So it never sees this infinite volume of ADS. The proposal in my paper with Dutta was that this area is computing this reflected entropy, or the von Neumann entropy of this canonical type 1 factor. Okay, so that was a proposal, and we gave evidence for it, as I said, using the replica trick. So let's assume it's true, and then we can give now an example where we can actually calculate this quantity. So for a 2D holographic CFT, we find that there's actually a universal answer, at least for the vacuum state. We can just compute the length of this curve using these geodesics, and this is what you find. It's a concrete answer. You get 2c/3 log times something that depends on x, where x again is this cross ratio of the 4 endpoints of the boundaries of these two intervals. So I have A and B. The boundaries of these intervals are 2 points here, and then these 2 points here. And so with that, I can form a cross ratio. And this reflected entropy just depends on that cross ratio because it's a CFT. Now, the factor in front is 2c/3. In a holographic CFT, C is always very big, so you have many degrees of freedom. And so this is the answer. It's really the leading term in some large C expansion. So there's going to be order C corrections. And interestingly, you find the answer 0 when x is less than 1/2. So when x is bigger than 1/2, you're in this setting where you have these this connected entanglement wedge. When x is less than 1/2, then you get these disconnected AB regions. And then the rule for this reflected entropy is that you should actually assign the reflected entropy to be 0 in the setting.
Thomas,
and so yes.
There is notification of the calendar in the top right of the screen, so maybe you would like to.
Sorry.
I don't know. No, it's just for you. Okay.
There's a notification. Yeah. My wife is dealing with that notification. Okay, very good. So now, okay. So when x. Okay, good. So when x is less than 1/2 and you're in this disconnected setting, then the reflected entropy, I should have written it here, is not 0, but it's order C to the 0. So it's small relative to this. Okay. Good. Now, you can take this formula and send x going close to 1, and you find this answer of minus 2c/6 log 1 minus x. And this is the famous Calabresi formula for entanglement entropy, or twice the entanglement entropy, actually. They found this sort of universal behavior in the entanglement entropy. And so the idea is that because this is becoming something that looks like an entanglement entropy in this limit, is that we should think of as SR divided by 2 as some kind of regulator for entanglement entropy. It allows us to compute the entanglement entropy in the continuum limit where we have some regulator, which is this sort of small region B here. This distance B between the two intervals. Another feature that you can see from this formula is that this is actually discontinuous. It's not continuous. It does it so as a function of x. When x is at 1/2, it jumps like this. And this is actually a feature that doesn't exist for other entropic quantities. This jumping of the entropy. And so the natural question, there are several natural questions here, but a natural question is, can we reproduce these features directly from quantum field theory? So good. So so this leads me to this first result, which is just sort of some follow-up work to previous discussions on reflected entropy, or this type 1 entropy for free fermions. So in particular, these references, Xu and Longo and Bueno Cassini, are really the people who's initiated this study, and I'm just going to make some extra comments. Okay, so consider a 2D, say, chiral fermion. We can also talk about Dirac fermions. In vacuum. Associated to that, I can compute a correlation function for the fermions psi dagger psi, and it looks like this: 1/2 pi I x minus y minus I epsilon with some I epsilon prescription. There's some canonical anti-commutation relations for these fermions, but it's known. It's a free theory. Free fermions are a free theory, so the vacuum is Gaussian. In particular, that means that higher point functions are determined by Wick's theorem. So all I need to know are the correlation functions of 2 fermions, and then I can compute correlation functions of any number of fermions. So this is also true restricted to subregions. And because of this fact, because I can use 2-point functions to compute any correlation function, that means that the reduced density matrix, which determines all correlation functions, is also determined by this correlation function. So this idea is sometimes called the correlation matrix technique, or the Peschel method, and is discussed by Cassini and Horta, and many others. And so, it goes as follows. So if I take my correlation function of fundamental fermions for an interval, so the correlation function that I just wrote down here, and I restrict it to the interval A, then this correlation function defines some integral kernel, and I can look for eigenfunctions of that kernel. So an eigenfunction would solve an equation like this, where I integrate over A, some function f, which is my eigenfunction, and then I get an eigenvalue lambda, where y is restricted to A. And so the eigenvalues of this, the claim is, this is a non-trivial claim of this method, is that the eigenvalues of this correlation matrix determine the spectrum of the reduced density matrix. In particular, the spectrum is just lambda I and 1 minus lambda I for these fermions, and for each of these eigenvalues. So for this single interval case that I just described, one actually finds a continuum of eigenvalues. So for example, if I take A to be the half space, then these eigenfunctions, the appropriate eigenfunctions look like this. They're just powers of x. with some imaginary power nu, where nu goes from minus infinity to infinity, and the eigenvalue is just this, which goes from 0 to 1. So the fact that you find this continuum is sort of the reason in this language the entanglement entropy is infinite. So we didn't find this discrete set of PIs that we were looking for. However, if it was a type 1 factor, we should find this discrete set. And so the question is, how does that work, and how does that work for this nice type 1 factor that computes the reflected entropy? Good. So I'm going to imagine, it doesn't really matter. The theory can live on the plane or the circle, but let me think about the theory on the circle, where I have two intervals A and B as shown here, and the idea, of adapting this correlation matrix technique to compute this reflected entropy would mean that we have to study correlation functions for the fundamental fermion psi of x, restricted to A, but also we should also include correlation functions where we have this mirrored fermion, where we take this JAB operator and mirror the fermion in A as well. So you can think of these fermions as describing the region A, and these fermions as describing the region A star. And so the idea, of adapting this correlation matrix technique to this problem is that if I know all the correlation functions of those fundamental fermions, then I should be able to reconstruct the density matrix. So it's not hard to show that these still satisfy Wick's theorem and the canonical anti-commutation relations that was discussed in this paper. Well, I find, at least in my mind, it convenient to unfold these fermions. So in how I just described it, we have two fermions on this region A, psi and psi hat. But if I just think of the psi twiddle fermions, or the psi hat, this is meant to be a hat, the psi hat fermions, as living in the complement region AC, and then I just undo that by including a CPT reflection, then I can introduce fermion psi twiddle of X, where X now lives on the complement to A. Where this JA here is just this CPT reflection associated to A. In the setting where A is just a half space, it's just a mirror reflection across here. Okay, so and so once you do this unfolding trick, the end result is you have fermion psi in A, psi twiddle in A complement. So that's just a free fermion living on a circle with NS sector boundary conditions. The only difference between the free fermions living on a circle in vacuum and this is that we should actually pick a different state. So it's not the vacuum state, it's a funny Gaussian state, which is determined by the correlation matrix, right? Just because it's a free theory. And so you can just write down what this correlation matrix is based on this argument. It's just determined, this correlation matrix for this psi twiddle fermion. So I introduced this notation where psi of X, which was the original fermion in A, I'll just call that psi twiddle of X when X is in A. And then the correlation function for these psi twiddle fermions, you can just work out. So if both X and Y are in A, then nothing happens. We just have the original correlation function for those fermions. Similarly, if X and Y are in A complement, then we mirror both the fermions, and then sort of this JAB factor just cancels, and we just get the same vacuum correlation function. However, if for the cross terms, when one of the fermions is in A and the other one is in a complement, then I think I have some, this is fine. I think there's a dagger here. There should be a dagger here. Okay. Anyway, for the cross terms, then we can just calculate what these correlation functions are in terms of this JAB. It's convenient to write it in terms of the Tomita operator delta AB. The modular operator delta AB to the 1/2, just using Tomita-Takasaki theory. And so in this cross region we have this correlation function with this delta AB. And similarly in the other cross region. So in order to calculate these eigenvalues that I've been looking for, all we need are these modular flow correlation functions for 2 intervals A, B. And indeed, those are available. I didn't put the reference here, but the original paper studying this was Cassini and Horta, but then it was studied more rigorously by Longo and Xu, and then Holland has a nice paper which derives this. And it takes the following form. So I can calculate these correlation functions with this delta AB to the IS. And it takes the following explicit form where A1, A2 are just the boundaries of the A interval, B1, B2 are the boundaries of the B interval. Good. What else? Yeah, so then all we have to do is take S and IS to 1/2, and so then we can calculate these correlation functions. And so that means we've got the correlation functions for the psi-twiddle fermions. So in principle, then we can just go ahead and look for eigenfunctions where we integrate over the entire circle. So we can do this and conveniently, we can do it numerically. So it's this correlation function, you sit down, you look at it, it's not that complicated, but there's no way to find, at least for me, to find an analytic solution. So the best thing we can do is numerically, if we just do a Fourier series on this function f of z, and then we truncate the Fourier series, and then we just have finite dimensional matrices and we diagonalize them, and we check for convergence. And so that's what we did. This allows us to explicitly calculate the reflected entropy SAA star as a function of x, and here's the red curve as the numerical solution. And for reference, I've put in the blue curve is the holographic answer where I've normalized by c. Okay, so you see this discontinuous jump, and you see that the actual form is very similar. This curve also agrees with Bueno Cassini, who studied this problem using the same idea, correlation matrix, but they worked on the lattice, not in the continuum. I was also interested in not just the reflected entropy, but also the spectrum. And so here's some pictures of the spectrum. So M is just the index of lambda I, and it fits nicely to this sort of tangent curve. So this is some specific value, fixed value of x of the cross ratio, very close to 1. And the different dots here are showing sort of convergence, or as we increase the truncation. So it's sort of for very close x close to 1, the convergence you can see is not great. It takes more larger and larger matrices to see this. Okay. Now we can get a slightly better handle on this problem. Sorry. We can get a slightly better handle on this problem using sort of analytic arguments in various limits. So we can analytically use this correlation matrix technique to calculate the answer as x goes to 0, and we find the reflected entropy goes like minus x log x times some explicit factor that we can calculate exactly. This was this x log x was noticed in Cassini Bueno paper, at least numerically. And so we can analytically extract this coefficient and this limit. This x log x is interesting in itself because other quantities like the mutual information always have algebraic powers here without this log. So that's sort of a new feature. The other interesting limit is x goes to 1. And so you can give, it turns out you can give an analytic argument in this limit. The naive thing is if I take x to 1 on this correlation matrix that I just wrote down, then it just becomes the following. You get step functions in the region A plus step functions in the region A complement with the original sort of vacuum correlation function. And so this sort of puts us back in the setting, in the original setting where we just had a single interval and we're trying to use the correlation matrix technique to calculate the entropy of that. It leads to a continuum. So in fact, we get a continuum of these Rindler modes with that continuous spectrum. The better way to do this is to take this limit a bit more carefully. So as x goes to 1, what you find is the correlation matrix has the following structure. This is in the ZW plane where Z and W are the two sort of fermion coordinates. And here I've sort of just imagined the setting where A is the half space. That's the blue region here, and the orange region is A complement. And the naive limit just gave a correlation function which was non-zero in these sort of purple regions. However, what you find is that there's some smoothing out of this step function very near the boundaries here, near the boundaries between A and A complement. So the idea is that as we take x goes to 1, we should zoom into this region and do something that looks a little bit like a matched asymptotic expansion. So what we do is as we send x to 1, we also scale our coordinates, and what we find in that limit is something that looks like the same correlation function, which is slightly shifted 1 over z minus w, and we get these shifted Rindler modes with some, in principle, continuous spectrum. But we also have to do the same thing for a very large z and w. And we find, again, a shifted Rindler mode. And we have to match those two Rindler modes smoothly in this region here. And when we do that matching, we find that nu is quantized. And so we can extract from this the quantized value of these eigenvalues of the reduced density matrix. And this is the value of nu. And if you remember from previous, I wrote it down, lambda is determined in terms of nu. The lambda are the eigenvalues that we're interested in using this tanh function. And so this answer that we found analytically agrees with the numerics here. And in fact, it has an interesting interpretation. If we just take these eigenvalues at face value, then the reflected entropy approaches the following form, which I can write in some thermodynamic way, determined by some partition function z of beta. And what is this partition function? It's the following product over q's, where q is the usual e to the minus i 2 pi tau, where tau is the modular parameter, for the partition function of the fermion. So in fact, this is just the ns partition function of the free fermion with some temperature, and that temperature is determined by the following modular parameter, which is then determined by this cross ratio 1 minus x. So indeed, the eigenvalues approach the spectrum of a thermal density matrix. And an interesting thing about that is that the reflected entropy this universal answer for this reflected entropy as x goes to 1 is then just a consequence of the Carty formula for the density of states and the high temperature limit of the CFT. This is not just some crazy method. We can systematically correct this expansion, so we can calculate corrections to this. But it should be remembered that it's only valid in the limit where the two regions come very close. So the conjecture we have based on this is that the reflected density matrix approaches that in this limit where the two intervals touch, approaches that of the thermal density matrix. At least the spectrum does. And so, it'd be interesting to prove this more rigorously. And perhaps most interesting is if this was much more generally true. You could imagine this statement being true for general CFTs, not just for free fermions. And if that conjecture, more general conjecture, is true, this is very interesting because you can extract CFT data, the spectrum in particular, this thermal partition function for the theory on a compact space, tells you about the spectrum of operators in the theory. And so directly from the ground state wave function, which is how you're defining this reflected entropy, you can extract this CFT data. And so this is useful for sort of numerics on interacting CFTs. And so, yeah, and so I'm out of time. So let me finish there.
So thank you for your interesting talk. So are there any questions or comments?
I can ask a question.
Yes.
Aito. So, nice talk. I would like to understand whether you, from what you have done, you have the information about this problem. When you have the split problem, the split property, then you have this intermediate type 1 factor, and we can compute the von Neumann entropy. Now, when the two regions they tend to touch, this von Neumann entropy explodes, but it should have some universal behavior. Do you have an idea of what you get?
Yeah, sorry. You mean, yes, yeah. So you find this is what I was describing here. I mean, this is the answer is that x goes to 1. This is what we find, at least. The reflected entropy approaches this universal form, and in particular, it does approach this -1/6 log 1 minus x, which is this Carty-Calabrese answer. Times 2. I might have missed a factor of 2 here.
Very good.
Yeah. So that's right. Mm-hmm.
Mm-hmm. Mm-hmm. This is published already.
No, it's not. It's a work in progress. So yes, it's also not to the level of rigor that I'm sure that you would like. But yeah. So the problem, reducing it to this correlation matrix technique, that I'm sure is correct. I don't think we've rigorously established it, but I'm sure it's correct. Then extracting the spectrum is what we're sort of doing, the new thing there.
Maybe I can make a comment, probably not important, but at the beginning, when you explain the split property, you make a picture about two wedge regions.
Yes.
It's exactly the case where the split property cannot hold, at least in higher dimension. Because if you have one parameter group of translation that leave this region invariant
yes.
by the cluster property, you cannot have, except in 1+1 dimension in the massive case. Otherwise,
Yeah.
So one should have, let's say, either a bounded region, including other bounds.
I should complete the diamonds. Yes. Okay,
Yeah.
that's fine. Yes. Okay. Thank you. Yes.
Sorry, my microphone was off. So next question. So was by, I can only read the name, so I apologize. Is Marius? Okay. So
yeah, that's me.
okay. Hello.
Yeah. So it's weird to actually ask a question to a colleague, which is virtually just across the street, but you know, that's life. My question is the refractive entropy. It's a kind of similar to Robert's, but beyond split property, is there any way to still define it?
Yeah, I mean, for matrix algebras, it's well defined. It's defined using this canonical purification.
And for type 3 objects?
Yeah. Oh, sorry. Beyond that. Oh, that's what you mean. No, I don't think so. I think it's probably not finite, or yeah. I think it needs the split property.
Okay, thanks.
Next question is from Feng Shu. Please. So I see hand raised by Feng Shu. So go ahead with the question if it's not a mistake. Okay, maybe it's a mistake. I don't know. Okay, so sorry?
Probably cannot hear.
My microphone is on, so I don't know. So Feng Shu, can you hear me? And did you ask a question? Would you like to ask a question? I can't hear any voice, so. So, other questions or comments? If not, let's thank the speaker again.
Yeah.